Welcome everybody to today's talk. In this session, we will introduce the mobile development best practices of Delta Force Mobile. My name is Jane. I'm the global lead of Qualcomm developer technology, and here we have the honor to have the Guihong Xu, the lead software engineer from Tencent TiMi Studio. Okay, and then let's also welcome Walker, the senior software engineer from Tencent TiMi Studio. Okay, so Qualcomm Snapdragon Studio and Delta Force has strong, long-time collaboration. So let me introduce a bit of background for this talk. As we all know, unified development across PC and mobile has been really challenging. It's become a mainstream trend. So it's been quite challenging to balance the high quality visual, stable frame rate, and low power consumption on a mobile device. Developers want to actually inherit the advanced assets and the complexity of PC games. So that's why we're having this talk. In this talk, we will provide some best practices and use case on collaboration between Qualcomm and Delta Force. We will share some in-depth knowledge on how mobile performance and power can optimize for cross-platform development. We will also introduce how you can leverage the Snapdragon 8 Elite Gen 5 platform, and we can go over the third generation of Orion CPU, Adreno GPUs, new 18 megabyte independent high-speed memory, and together, Qualcomm and Delta Force, we will work together on optimize the complex textures and everything on these battle scenes. So we want to achieve higher bandwidth, efficiency, and stable frame rate. And on top of that, I want to mention that we are able to maintain a top visual quality as well as effectively control the power usage and device temperature. So that's a key for our mobile development. Okay, so without further ado, let's welcome the Delta Force engineers to the stage.
Hi everyone, my name is Guihong. We are both from the Delta Force team, TiMi Studios. I will start by giving you a quick overview of what Delta Force is all about. Delta Force is a cross-platform FPS game and we offer multiple core gameplay modes, including large-scale combined and battle cross land, seed, air, with multi-vehicle coordinations, as well as a three-player tactical ejection mode we call search, strike, extract. As you can see, the gameplay is rich and the scenes are very complex. Now that you know how to play the game, and let's go over it. There are a lot of complex systems behind the scenes that make all this possible. Engine foundations, providing rendering system and low-level capability support, access production pipeline. Our complete creations, workflows, and toolchain systems. Gameplay systems, implementing our cross-platforms core gameplay logics. And outdoor game systems, including weapons, customizations, social intelligence, and matchmaking modules. And finally, performance optimizations of both mobile and PC platform. Now, given the time limit today, I will focus on what we consider the most practical part, how we achieve the balance between achieving performance optimizations and realize the visual qualities on mobile. Delta Force uses a unified development approach for both PC and mobile platforms. That makes it possible for us to develop things for both desktop and mobile, or within a single environment. As this creates a core challenge for us. How do we perceive the PC quality visuals on mobile will ensure excellent performance on mobile device? These are the key challenges we face on mobiles. First, game sync performance and memory optimizations. Second, mobile rendering, inference, and GPU performance optimization. I will cover the first part, and then I will hand it to Walker. Let's start the game sync performance, and memory optimization. Here's one of our typical game scenes titled. You can get a sense of visual qualities and comparison with during weight. The S quality across the entire scene is quite high, and the object placement density is also very significant. Moreover, the density isn't just horizontal. We also have substantial vertical access densities. What's more, the method contains very rich in those charge. We can just migrate the things from PC to mobile. Let's look at the original level assets created by our arc team. We have a large arc team, so we didn't impose many limits at the original level stage. Artists could create their own sublevels according to their need, with only simple functional layerings from the engineering side, so the divide sublevels and out quick sector and outlines. Also, for materials and texture reuse, a single static mesh in our pipeline can contain many sections. That's Unreal's original approach, but it has a significant impact on performance. In the tight side, which is only 300 by 300 meters, we have to deal with an extremely high on numbers of actors, components, and overall asset. There are two main approaches to handling such a bigger world in our industry: level streaming and culling. Level streaming usually means streaming based on distance, and culling usually means SoC and PVS on mobile platforms. Here's SoC reference to software occlusion culling, and PVS stands for pre-computed visibility set. But here's the question: is that enough? Well, for therefore, the answer is far from it. You see, during the active productions, we don't constrain our artists to sub-level design or density rules, because quite frankly, that's difficult for them to understand. However, we find the most levels are loading into memory anywhere if we just use the settings from artists. It was a disaster. We still have hundreds or thousands of visual components even with excellent culling. Assuming each component generates an average of 5 job cores, we are looking at thousands of job cores on mobiles. The heaviest CPU overhead leads to huge power costs on mobile devices. Additionally, overheatings and French job could likely result from it. To address these issues, we implemented 4 key techniques: high-performance scene pipeline, resource recompositions, scene feasibility pre-computations, optimized junk via SAGC. Because the original game scene is quick to get, so we need to make the runtime scenes more stretched to support more precise streaming. It leads to our first approach: high-performance scene pipeline. In this pipeline, there are 3 key points. First, we format sublevels according to predefined rules for hierarchical divisions, categorizing based on the asset size, whether they are decorations, and so on. Different hierarchical levels can have different size. And second, we do performance optimizations on the level components to remove unused components, to merge same type static mesh component to ISM in nearby regions, to discuss shadows in those components, and so on. In short, we prepare visibilities for better runtime currents, and the PVS plays a critical role in runtime performance. Please pay attention to the PVS, which is sort of pre-computed visibility set. That's an important technique that could be mentioned many times later. We pre-computed the visibility for components in different positions in the scenes. We back the PVS cell ID list and the invisible components ID list for each cell. The size of each PVS cell is equal to 1 meter in the real world. This shows our sublevels after the construction pipeline processing. As you can see, all sublevels are now divided according to our guidelines, which enables more precise level streaming. The table here shows our different sublevels in hierarchical breakdowns, including the size and loading settings for each layer. All right? After going through the construction, pipeline processing, level streaming, and previous calling, the game can actually run on mobile device, but only on high-end device, and the performance is still far from acceptable. Look at the columns in pipeline in precision. One of our things will have 320 draw calls just for static things itself. Draw call can even higher when character, weapons, and the UIs are added into gameplay. More draw call means more CPU overhead, and is less to head generations on mobile. We have too many sessions per static mesh asset. We have to reduce the sessions. How do we solve this? Our solution is resource recomposition, which means batch as many as you can offline. There are three key aspects of resource recompositions: texture atlas, materials batching, and model batching. Here's the challenge. It requires close cooperation from our art team. If a set creation is not standardized, the results will be quick pulls. At the same time, where batching does reduce draw call, it also increases vertex overhead, which needs to be balanced. Additionally, it needs to increase in package size and memory use. Let me walk you through it. The first step is texture batching. We collect texture from static mesh in the scenes and combine them together to the atlas. And these are the two core objectives here. First, minimize the numbers of texture atlas after merging, because different atlas generate different draw call. And second, avoid the texture redundancies to reduce package size and memory. We are building an open world scene with different POI areas, and we also have a shared texture resource. Because on this, we set up some atlas rules. We ask our artists to manage the textures by themes, distinguish between shared map textures and POI special textures. In this themes, consent is quick, easy for artists to understand and execute. Now for materials batching. There are two conditions for materials batching to the tag effect. Texture must be identical, and materials parameters must also match. To improve batching effectiveness, we implement some parameter mergings for materials, storing them in the batch material Eastern parameters list. We also impose some constraints on how artists use these materials. For example, limit overall varieties of wood materials type and standings on how materials in certain parameters are used. Next is static mesh batching. This comes in two approaches. First, introduce static mesh batching, merging multiple sessions on each static mesh generates only one draw call. And second, close static mesh batching, merging multiple static mesh from nearby components. The trade-off here is increased vertical cost, package size, and memory. We impose distance-based rules according to our streaming strategies, as shown in this diagram. For nearby static mesh, requires a high precision. We only perform ensure static mesh batching combined with current. It reduces a large draw call and without any size effect. For mid-distance static mesh, we use the lowest LOD levels for close static mesh batching. The lowest LOD has very low precision, and the impact on package size and memory is quick limit. For the further static mesh, we batch them all together with much simple models. Write one draw call for all distant models in one level. As you can see, in the table on the left, that's the combinations of static mesh batchings on different layers. Additionally, to support the very low-end device, we generate low quality levels for certain layers. These low quality levels use LD1 static mesh for nearby batchings, more than aggressively reducing the draw cost. As described in table on the right, for each quality settings, we use a different streaming strategies by combinations of different layers to satisfy the performance needs a variety of devices. As the data shows, since draw core draw from 320 to 210 after override static mesh batchings, CPU overhead is well optimized, and we can place smoothly even on a very low-end device. However, there are still challenges in the things. First, there are still too many components, and the render thread has to handle every component with extensive calculation. Second, there are still too many static mesh and hitches, which cause massive memory use. What should we do? We don't want to ask the artists to reduce scene resource as much as possible. That could seriously hurt visual quality. Let's think about it from another perspective. Why are there still so many resources? And look at this video. Although we are currently in dot and can see very few assets in our field of view like this, and there have many invisible sublevels in the place, but we can see them. So now the problem becomes too many invisible sublevels sitting in the memory. Traditional distance-based streaming can't solve these problems, and perceived regions controlled loading approach also struggle with these issues. Our optimization goal will become clear. Unload these invisible sublevels from memory. But how can we achieve this? So we tried a room-based loading approach. The plan was to extract indoors static mesh and other resources to the same levels, and have level artists to place trigger volumes at edges, like dots and windows. Looking could only occurs when players enter these triggers. Now, in series, the approach could handle streaming for things with extensive indoors areas quite well. But in practice, our level artists all really struggle with this. Our things are just too compressed and less to frequency deployment error. We also tried other approach, but none could be effectively implemented. So let's review what PVS does. PVS data indicate which components are invisible at special positions. Now the question becomes, at any given positions, what sublevels have all their components invisible? Using these rules, we can precisely determine which sublevels are invisible and safe to unload. Okay, it should be working, but there's still one remaining issues. Our sublevels are devices use fixed size in space, which means we can't effectively distinguish between indoor and outdoor areas. As you can see from this diagram, many of our sublevels contain both indoors and outdoor components, and the room across multiple floors get assigned to the same levels. This makes it difficult to achieve the more precise streaming optimization. So we have to come up with better ways to devise our sublevel. Going back to PVS raw data, it's recall a relationship between a position and invisible components, so we can get all of these invisible positions for a given component. Now, for components that are inside the same rooms, their invisible position data share an inherent similarity because they tend to be hidden from the same set of viewpoint. Based on these principles, we can leverage PVS data to devise our sublevel. The first step is to cross the PVS data. First, we perform reductions. We merge the component invisible PVS cell ID list into PVS block ID list. We greatly reduce the data size. And second, we apply greatly rule to class the components together while minimizing the different weighting each class. And third, based on this class group, we can consider one group for components to have a similar visibility. And then combining with our original special region device, we create a new sublevel. And the second stage is post-processing on generated sublevels. First, we implement an algorithm to score the device levels. And second, we left abnormal component in a separate group for special handling. And third, after splitting, we continue evaluations, split, evaluate, and loop until to find the best variant. For example, the chart shows the culling growth distributions by different splitting measures with varying numbers or sublevels. You can see there is a 3 point. We need to find the best variant. As you can see from this diagram, using previous guide level splitting, we're able to separate the individuals in dots and levels quickly, effectively. So, finally, after finish our previous guide sublevels visibility cullings, the result was very significant. Almost all resource low in memories disgrace obviously. We saw substantial reduction in components, static mesh, and texture across the board. Because our scenes are very, very rich and our streaming is fine-grained, sublevel loadings and unloading becomes frequent, leading to frequent I/O operations and sometimes cause frame drop and junk. Junk is the sudden, unexpected interruptions or what was otherwise smooth motions. Beyond the level streaming, operations like character corrections, spawn UIs, and garbage corrections on are also trigger junk. We can handle it with SAGC. When games run on the mobile device, CPU cores typically don't operate at the max frequencies. There are two reasons. First, is waste performance, and second, is less too high power consumption. Now, Qualcomm's SAGC provides us with a capability. We can notify the chip hardware in advance to temporarily boost core frequencies, meeting our peak performance needs. For example, before executing the garbage corrections, we can call the QAP boost CPU functions and pass it in a CPU frequency boost radio. This allows us to control the CPU for short-term frequency splitting. As you can see from the videos, with proactive CPU frequency splitting, we can remove the disjunct during gameplay. Okay, so that covers the core scenes optimization challenge we face and how do we solve them. Let me hand it over to Walker for the second part. Thank you.
Hi everyone, I'm Walker. A little bit nervous though, yeah. So I will pick up where Guihong left off and dive into the GPU and rendering optimizations we've done for Delta Force on mobile. Before we get into the details, let me quickly walk you through our rendering pipeline on desktop. So you will have a better understanding of what we are up against on mobile. Yeah. On desktop and console, Delta Force uses a classic deferred rendering pipeline. Essentially, the rendering process breaks down into the multiple stages. First, the scene setup, which includes depth prepass, HZB construction, shadows, and more. And then comes the surface stage. That's exactly where we handle the debuffer, gbuffer, and custom depth. This is where we prepare all the data the lighting needs later. And there comes the lighting. That is the most critical stage, and which covers the ambient occlusion, direct lighting, indirect lighting, and global illumination. A lot of things going on there. Then we have the reflections and translucency, followed by post-processing with TAA, tone mapping, various visual effects, and finally the user interface on top. So, in other words, the final image you see on the screen is built up layer by layer. with data stacking on the top of one another. Now, please pay attention to the little boxes there. Each one of these steps in practice corresponds to a render pass transition, which means the memory bandwidth overhead on mobile. For desktop, which has dedicated video memory, that is totally fine. In fact, splitting the work across multiple render passes and running them in parallel with multiple command lists, that's exactly a classic optimization. But here's one thing. The entire methodology doesn't work on mobile, and it can actually make things worse. So what's the most crucial differences between the mobile and desktop? You might immediately think of the performance gap between the Android, iOS, and desktop, or maybe the differences between the APIs, GLES, Vulkan, and DirectX. But from my perspective, the most fundamental difference is the power consumption. Mobile devices don't have the luxury of a stable external power supply or aggressive cooling like desktops. Yeah, and take a look on the chart on the left. That's one of our mainstream devices after running under a heavy load for an extended period. You can see the frame rate starts with small spikes and then, boom, it drops from the 60 frames per second down to around 55. That is a textbook example of thermal throttling. The device overheats and the GPU is frequency capped and the frame rate becomes unstable. Keeping the power consumption at a sustainable level is absolutely critical for maintaining playability. Yes, I mean, it's very serious, playability. Many factors contribute to the heat generation. Besides the CPU-related aspect Guihong covered earlier, and the bandwidth and GPU workload are the most common. It means the rendering optimization on mobile is not just about computation. You also must take the power consumption into account. And honestly, power often needs to be the top priority. Now, look at the diagrams on the right. It shows the divergence between the growth of computing power and the memory bandwidth over time. The yellow curve shows the compute capability, and the blue shows the memory bandwidth. The gap between them are widening. Expensive bandwidth and limited GPU horsepower, there are two core challenges we face when optimizing rendering on mobile. Given those two core challenges on mobile, and the first thing that comes to mind are just simplifying the materials, reduce the real-time lights, and lowering the resolution. But is there really enough? As a cross-platform shooter, Delta Force Mobile's visual must maintain a near desktop quality. And in the meanwhile, as an intensively competitive game, the frame rate is essential for gameplay. So there leaves us in one path forward. We must restructure our rendering pipeline for mobile hardware, maximize the use of tail memory, leverage the latest hardware features to reduce the bandwidth, and bring in the advanced technologies to reduce the GPU workload whenever possible. So let me just start with the bandwidth optimization side. I refer to Delta Force's mobile-friendly rendering pipeline as light HDR. Yeah, and the meme pretty much summed it up. While making the most of mobile hardware features to save bandwidth, it still maintains HDR rendering. The first step in light HDR is to merge the scene rendering. I refer to everything between the shadow pass and the post-processing as scene rendering. On mobile, instead of separating the surface and lighting into distinct stages, as we do on desktop, we do everything in a single render pass as possible as we can. The benefit here is straightforward. We keep as much data as possible in the tail memory and avoiding the bandwidth overhead of the render pass transitions. Now, what about the decals? Well, most of the decals in Delta Force are things like dust marks on the walls. Static effects there are already been handled during the resource recomposition stage, which was mentioned earlier. But what about the runtime dynamic decals like graffiti? Yeah. And that's solvable too. We use subpass load, or frame buffer fetch combined with depth substantial fetch on GLES to read the colors and depth directly from the tail memory and then apply the decals to the surface. And I really want to highlight this. Subpass load is an extremely important technique. When used properly, it lets you accomplish a lot of things directly in the tail memory, otherwise require extra render passes transitions. Many of the optimizations I will be talking about later are built on the top of it. So similarly, the translucency doesn't need its own render pass either. We just join it right after the opaque geometry, and that's it. So at this point, we have merged both surface and lighting into a single render pass. That's a great start. And I want to talk about the post-processing here. As an intensive competitive shooter, Delta Force frequently overlays screen effects to indicate the player's state, such as under attack or injured. Take a look at the image on the right. Yeah, that is a player running while injured. And you can see the multiple layers of post-processing effects stacked around the edges of the screen. The traditional post-processing approach writes the entire scene to the system memory, read it back, and then append the screen overlays on top. But here is the question. In many cases, these effects don't actually need to sample the pixels from other locations. There are just simple animations, flowing patterns that get blended on the top of the scene. So we replace the traditional post-processing with screen meshes. Yeah, that is exactly a mesh in front of the camera. And technically, a full screen quad that join in a subpass right after the scene rendering and before tone mapping, all within the same render pass to achieve nearly identical post-processing results. When we completely avoid the bandwidth overhead of writing scenes to system memory and reading it back, that's another solid win. But we are not done yet. In the post-processing stage, besides the screen overlay effects, there are also auto-exposure to deal with. In recent years, auto-exposure has become an essential feature for high-quality mobile games. The principle is pretty much straightforward. You read the color data from the render scene and compute the overall brightness and then scale the image to a range that looks natural to human eye. It works just like your eyes do. When you walk into a dark room and everything is hard to see at first, but pretty soon, your eyes get adapted and your vision becomes clear. The problem is that this full screen color sampling happens every frame, and it consumes bandwidth. But think about the algorithm, what algorithm actually needs? Just an average brightness value. Do we really need to sample more than 2 million pixels to get that average? We look at the Monte Carlo methods. The core idea is simple. Random sampling can still capture the key shape of a distribution. So we downsample the scene instead. Each 16 by 16 block output a single luminance value into a small buffer. And we compute directly from that small buffer. In the vast majority of cases, the results are almost identical to the original approach. Plus, human eyes naturally adapt to the changes in brightness over time. If you can tolerate a little bit of latency, you can even use the small buffer from the previous frame. All right. So with the auto exposure before tone mapping and the screen effects after tone mapping handled, we are left with the most critical piece, the top mapping itself. On mobile, Delta Force scene rendering still operate in linear space with HDR. Remember? Because we want to maintain the visual quality on par with the desktop version. The user interface, however, stays in traditional SDR to preserve the existing design workflow. So before we draw the UI, we must do our top mapping first, to converting the value from HDR to SDR. In theory, this step can't be skipped. Can we bypass this? Yeah. Combining the scene rendering, post-processing, auto-exposure, top mapping, and UI into one render pass will be very ideal. And yes, it's possible. Once merged, when the scene resolution matches the back buffer's resolution, we just need one render pass to handle everything. Bandwidth reaches its minimized. Yes. And for now, let's consider the case where the resolution match. The back buffer is the most natural render target for this. But here's the question. How do you store the HDR values on an SDR format back buffer? SDR buffers store values between 0 and 1. That's it. While HDR values can exceed 1.0. A sunlit surface might be 0.5, I think, and a specular might be 10. If you write those values directly into an SDR buffer, anything above 1 gets to clamp to 1.0, and all the information, all the range, that is gone. That's data destruction. So, how do you store the HDR values in an SDR buffer? Many people will tell you RGBM, RGBE, and log love. But either the shader math is too expensive at runtime, or they don't just make good use of those bits, and you end up with color banding. Our solution? Yeah, a simple curve. And I mean embarrassingly simple. Now look at the curve. The output should always be in the range between 0 and 1, right? It's very simple. The K parameter controls its shape if the K is small, just like in the left picture. And HDR input of 4.0 goes to about 0.8 in the buffer. And the specular value of 9.0, that goes to about 0.9. There are still differences between the bright stuff that exceed 1.0. The curve gets steeper while the K is big, just like in the right picture when K is 5. The same 9.0 specular now maps to 0.97, and a 4.0 is already at, I think, 0.95. The SDR outputs are almost the same. However, this situation is reversed when we look at the small HDR inputs. So, in short, small k preserves the bright details, and the large K maintains the dark details. And we adjust K dynamically based on the potential brightness and preserving as much detail as possible. Here is the question. What if the back buffer's resolution does not match the scene resolution? For instance, on devices with larger screens like the flagships, we do not want the UI to look blurry. In that case, we can't merge the top mapping and UI into the same render pass anymore. What do we do about the bandwidth hit? After top mapping writes out and the UI pass immediately need to read it back in. And under the traditional architecture, it seems an unsolvable problem. Well, Qualcomm's Snapdragon 8 Gen 5 brought us a breakthrough solution, tile memory heap. Tile memory heap provides a set of APIs that solve the last mile problem. These APIs allowed us to place the textures and buffers directly in that tile memory. So we no longer need to write the scene to system memory and reading it back. Here is the pseudocode. And as you can see, Just a few of lines. It's very easy to implement. We currently have the scene placed in the tail memory heap. And under our typical HD 120 frames per second and 1080p configuration, we achieve a 5.7 reduction in the total power consumption. And yes, that's without sacrificing any visual quality or reducing the resolution. The results are very satisfying. And we also plan to migrate more data to the tail memory heap and further extending the power savings. All right, with all that covered, let me wrap up this session. When it comes to a mobile power consumption, the bandwidth is a major factor. Here are the key takeaways from Delta Force's mobile rendering pipeline optimizations. First, for effects that can be achieved with a more power-friendly way, just avoid using the traditional post-processing workflows. Second, merge as many render passes as possible. That is very important, including the scene rendering, auto exposure, tone mapping, and UI. Third, for render pass transitions that are truly can't be avoided, use tail memory heap to eliminate the bandwidth overhead. So that covers the bandwidth optimizations for rendering pipeline. Now, what about the other major source of power consumption, the GPU itself? GPU workload is also a very significant factor in heat and power drain. And I will break this down into key areas. First, when you're playing a game, it's pretty easy to notice that not every pixel in the screen has a widely different color. In most cases, pixels within a small range are very similar. For example, when a character is in an outdoor environment, the surface of the metal container, the sky, a dam in the distance, their colors are extremely close. And sometimes the pixels are almost identical. So naturally, you start thinking, can we have the GPU shade just once and view the result into the multiple pixels? And the answer is yes. Modern mobile devices now support VRS, variable rate shading. In simple terms, VRS lets a larger block of pixels to share a single shading computation, and that result gets applied to every pixel in that block. So the problem becomes, how do we identify these visually similar regions, and how do we measure how similar they are? Our approach is to divide the screen into small tiles and then group them into larger ones. Each small tile records its luminance during the previous frame. In the current frame, we compute the color variance among the fragments within each tile. If the color variance within the tile is very small, that means the pixels are visually similar, right? For those tiles, we can apply 2x2 or even 4x4 VRS shading rates. Take a look at these two images below. The left image shows the downsampled luminance output from the previous frame. Even though we don't have the full color data, we can still roughly reconstruct the scene's brightness construct. And the right image shows the color variance computed from the left. Black means dissimilar, dark red means similar, and the bright red means very similar. You can see that large areas of the sky are highly similar. Many flat surfaces in the scene, as well as the rough mechanical parts of the player's weapon, also shows a lot of similarity. All of these regions can directly benefit from VRS and save GPU workload. But is that enough? How about the black areas? For instance, Distant and foreground trees may have different stripe color, but visually, these differences are insignificant to the player. Can we optimize this? Extensive testing confirm we can. So the solution becomes quite clear. First, we dump sample the luminance directly into a small buffer. Second, before the next frame begins, we compute the shading rate based on the luminance differences and generate a VRS attachment to apply the VRS. Third, for distant objects, we additionally apply VRS on a case-by-case basis with its LOD level. Of course, this approach isn't perfect. When the camera moves aggressively, using the luminance of the last frame can be inaccurate. In those scenarios, it falls back to a more conservative shading strategy. And let's take a look at the results. The performance gain from VRS are quite satisfying. Yeah. Still under our typical HD 120 frames per second and 1080p configuration, the visual difference is barely noticeable. And we gain 3 additional frames, and the GPU clock was reduced by 12.6%. It's amazing, right? And now, let's shift our perspective from a single frame to a continuous stretch of gameplay. The buildings and grounds in front of the player get rendered every single frame. But if you look closely, you will notice the terrain and the trunk in front of the player haven't actually changed at all. Only the player is moving. The surrounding scene have merely shifted on the screen. So naturally, the question arises, can we reuse the pixels that were already been shaded in previous frames? That brought us to a frame interpolation. The frame interpolation has been well used in the TV industry for years. And at its core, it's about generating the new pixels from existing ones. However, the interpolation introduced input delay, and the extrapolation introduced ghosting. According to our extensive tests, both of them are unacceptable, and especially for a shooter. But still, we can borrow the underlying idea. What if we just separate the static scene element from the dynamic ones? Doesn't that solve the problem? Static scene elements don't move on their own. Any position change on the screen must be caused by the camera movement. And the game engine keeps transforming 3D objects from the world space to the screen space. That transformation is visible to us. All we need to do is to take the previous frame's image, use the camera parameters from that frame to unproject it back to the world space, and then reproject it to the screen space using current frame's camera, so that we can reuse the pixels that were already been shaded. For dynamic objects, characters, weapons, and so on, we render them normally, just like before. So our dynamic frame prediction approach becomes clear. First, we are not doing a frame generation. We are reprojecting the static scene. Second, we reuse the static scene. Third, we render the dynamic objects, such as enemies and characters, normally. And it's critical. The game still runs at 120 frames per second. No input delay or ghosting introduced. It achieves an inter-frame reuse of static scene element. There are still many more details to this approach, but due to the time constraint, I won't go deeper into it here. The performance data was also very impressive. The frame rate increased by 10 frames, while the GPU clock actually decreased. Ultimately, we achieved a 14% 14% reduction in the GPU workload. And if you push the quality settings higher or increase the resolution, the gains become even more significant. So we have optimizations along 2 dimensions. On the one hand, within a single frame, we identify the regions with similar colors and minimal visual difference and use the VRS to shade less. On the other hand, across frames, we use dynamic frame prediction to reuse the previously shaded color whenever possible. Can we combine the two? Absolutely. And in practice, combining them produce excellent results. Still under our typical HD 120 frames per second, 1080p settings, with no material simplification, the GPU workload was dropped by 26%. It's huge. And that is what truly makes high-quality visuals at high frame rates a reality for mobile. Let me summarize the Delta Force's work on reducing GPU workload through the advanced rendering features on mobile. We fully leverage the spatial and temporal coherence. The GPU optimization is not just about reducing the computation and the computational complexity. It can also come from the reusing the pixels that have already been shaded. For mobile devices with limited resources, we're essentially dancing in chance, allocating the resources to what matters most based on the current gameplay needs and the visual requirement, while optimizing the performance in visually unnoticeable area. At its core, this is an art of balance. Delta Force's optimization journey on mobile is just the beginning. And in the coming releases, we will push visual qualities even further. More realistic light and shadow interactions, more convincing reflections, and richer geometry details, alongside more diverse gameplay experience, including more destructible objects and beyond. At the same time, 120 frames per second has evolved from a nice to have into a baseline expectation for competitive shooters. How to improve the visual quality and enrich the experience while maintaining the excellent performance, and doing so with enough scalability across different devices. That is the challenge ahead of us. So stay tuned. That wraps up the presentation from Guihong and me. Thanks for attending this session, and I'm gonna return the stage to Jen.
Okay, so that was amazing sharing. Thank you, Guihong and Walker. So I'd like to introduce our teams, and we want to provide you some takeaways from the Qualcomm Snapdragon Game Studios. So listen to what Guihong and Walker just shared. You might wonder, like, how can I get resources for those solutions? And I'm developing my own project, and how can I learn best practices to actually implement into my own project? Okay, now let's jump to the Snapdragon Toolkit. So just scan this QR code, and you can check what's available on the Snapdragon Toolkit. So we provide like extensive documentations and tools and resources for developers. And then you can also find, we have our GitHub Snapdragon Unreal Fork. So as the Snapdragon Studio, we prioritize on getting new features actually and merge into the engine, the Epic Unreal Engine mainline releases. So we also maintain some changes on our own GitHub fork if you want to learn more about the latest features and how would it incorporate into your projects. So we might run out of time, so I don't know if we have time maybe for just a few questions. You can also connect with us through the Discord community group, and we can maybe take a couple questions if we have any. If you want to ask questions, you can probably walk to the mic.
Are there any in-room questions for either Walker or Guihong or Jane? Yes.
Performance improvement. Do you guys are looking at super resolution to get more performance out of your GPU pipeline? Super resolution. Have you looked into that?
Super.
That is a good question. And the super resolution is a very good method to improve the performance and visual quality. But the competitive shooters, for our game, we don't have the motion vectors.
Okay.
So we are not able to just scale it in the right way. And it will be very, very heavy, and it causes much bandwidth overhead for us to append the motion vector to the game. So if you want to use the super resolution, you must base on your own needs. And please take care about the bandwidth optimization.
Yeah, thank you. That makes
Yeah.
sense.
Hello. So a function that a mobile device has and PC usually doesn't have is vibration or haptics. So I wonder if you applied haptics or vibration to the mobile version of your game. If not yet, do you have a plan in the future?
I think I didn't catch it.
Like, for example, if the user shoot and then the mobile phone can vibrate, will that be a better user experience?
I think to help shape your question, please correct me if I'm wrong, when taking into consideration overlays for indicators or enemies, do you also take into consideration things like haptics or screen shake when you're layering your frames? Does that make sense?
有没有考虑些什么震动提案啊，或者其他的一些反馈在你的移动这个版本上面？
We don't have the variation so far. It's still under consideration. But from our test results, the variation is not always a good thing for the player. Yeah, so you need to take care of the effects and do some research maybe.
Sure,
Yeah,
thank you.
We are still on it and it's under consideration.
Sure, thank you so
Yeah,
much.
Thank you.